In this mini lecture, we're going to talk about atomic behavior and how the behavior of an atom leads to the bonds that it will form with other atoms. You're looking at a picture here that was taken in 2011. And what's so amazing about this photograph is it is an actual image that is showing you how electrons are buzzing around a particular molecule. So you can see them right here. Up until 2011, or actually in the early 1900s, we had a really good idea of how electrons orbited around the nucleus of an atom. And most of our knowledge has been based on hypotheses and models. So these photos are actually really, really amazing now that we can visualize them and actually see that our hypotheses were not that far off. This image is even more recent. It was taken in May of 2013 using a quantum microscope. It is the first image ever of hydrogen, of the atom hydrogen, and the first image to really show how the electrons buzz around the nucleus of an atom. Now, as I mentioned before, this is of the hydrogen atom, so it only has one electron. So all they had to capture here was the movement of just this one electron and how it moves around the nucleus of the atom. In a moment, we will learn the structure of the other orbitals, and those images I imagine would be quite difficult to capture because as you increase in the number of electrons, the movement of those electrons around the nucleus gets increasingly more complex. Here I'm going to refer you back to an image that we looked at in our textbook. Okay, this is a very simplistic image of an atom, and this is showing just one orbital, okay, but we still have our nucleus, and we still have this orbital moving around the nucleus where the electrons are. And it looks very, very much like the image we just looked at. So I wanted to return to it to show you that, again, it's pretty amazing that our models and our hypotheses are not that far off. Okay, so the behavior of an atom is all based or determined by its electrons. Electrons have a lot of energy, it's potential energy. We know that electrons carry a negative charge, and the nucleus of an atom with protons and neutrons carries a positive charge. So the electrons are attracted to the nucleus. Electrons occupy what we call discrete electron shells, and these shells are areas in space where you're most likely to see an electron. Often you hear the word orbit used. I like to get away from using the word orbit because electrons don't actually orbit, meaning they don't, if this is the nucleus of an atom, they don't continuously circle around the nucleus. Okay, rather they buzz. Okay, so they're buzzing around, and the shells are where they're most likely to be found buzzing around at any particular time. An electron's energy level is correlated with the distance it is from the nucleus. So the greater the distance, or the higher the shell, okay, the further they are from the nucleus and the more energy they have. Your textbook uses a great analogy for the fact that as electrons move further away from the nucleus, they have a greater amount of energy. And the analogy is the ball on the staircase. So the higher the way the ball is from the floor, the more energy it has. But if you were to place the ball on the first step, it has less energy, it just drops from the first step to the floor than it does if it's up on the higher step. The reason why it's important to understand this is that sometimes electrons can move to higher energy levels. For example, light. Light actually causes electrons of certain chlorophyll molecules in a plant leaves to get excited and go out to a higher energy level. And that's the basis of photosynthesis, and we'll learn about that later on in the semester. Okay, so now we need to talk about these electron shells. So again, the electron shells are where you're most likely to see an electron at any particular time. Each shell is composed of orbitals, and each orbital can hold up to 2 electrons. Okay, so these are really important facts. Each shell is composed of orbitals. Each orbital can hold 2 electrons. Okay, now here's another important detail. The first shell has only 1 orbital. So that means that the first shell can only carry a total of 2 electrons. The second shell, and the third shell, and the fourth shell, all other shells have 4 orbitals. And if each orbital can carry a maximum of 2 electrons, then each shell, after the first shell, can carry up to 8 electrons. Regardless of how many electron shells you have, the outermost shell is called the valence electron shell. And this is the most important shell. All of its electrons are referred to as valence electrons. The goal of an atom is to have a complete valence shell. So if an electron only has one shell, its goal is to complete that valence shell and carry 2 electrons. If it has 4 electron shells, it doesn't matter. Then it wants to complete its valence shell and have a total of 8 electrons when in its outermost shell. This is what determines chemical bonding, because an atom is going to do a number of different things to accomplish its goal. Okay, so let's say we have a hydrogen atom. Okay, I'm just going to make this red blob its nucleus. I'm going to make this black line its shell. And right, we said that the hydrogen atom only has 1 electron. So this is the first shell. The first shell of any atom has only 1 orbital and can carry a maximum of 2 electrons. The goal of this hydrogen atom is going to be to complete its valence electron shell. So a number of ways it could do it. It could give up its 1 electron. It could share an electron from another atom, which we'll talk about how that happens, or it could steal an electron from another atom. That's why it is the electron configuration of all atoms that determine bonding. Okay, so here's another example. Okay, we're going to make this blue blob here the nucleus, right? And the nucleus, we all know, contains positively charged protons and neutrally charged neutrons. Then we're going to draw a first electron shell. And this particular atom that I'm going to draw has 3 electron shells. Okay, so the first electron shell can carry a maximum of only 2 electrons. The number of electrons that this atom has is 11, and the atom that I'm talking about is sodium. So we have to complete this model, this atomic model, and this is called the Bohr model. It's very simplistic, it's only 2-dimensional. This is really not at all the way an electron orbital looks, but it works for the simplicity of visualizing electrons and for understanding how bonding works. So we have 2 electrons already. Our second shell has a total of 4 orbitals, which means we can draw in 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. That brings us to a total of 10 electrons. Well, this is sodium. It has 11 electrons, so I need to make another electron. Now the goal of this atom is to complete its valence electron shell. So either it needs to find 7 more electrons to make this outer shell have 8, or it needs to get rid of this electron. And what sodium does is it does give up that electron. And when sodium gives up that electron, it ends up having or carrying a positive charge, because suddenly it has more protons than electrons, so we say it's positive. So often you'll see sodium written with a plus sign after, and that means that it is an ion. Any atom that carries a charge, whether it be positive or negative, is called an ion. Okay, so an ion is when an atom has an unequal number of protons and electrons, and therefore it's either going to be positive or negative. If it has more electrons, it's negative, and we call it an anion. If it has more protons, it's positive, and it's called a cation. And I like to remember this by thinking positively, right? And I think, oh, I like cats. So cations are positively charged. So that means that our sodium ion we just drew before is called a cation. All right, so now we're going to do another example. This time we're going to draw the atom chlorine. And chlorine has 17 electrons. Okay, so we'll make this red blob its nucleus. It carries positively charged protons. Okay, then we're going to say, all right, it's got one electron shell, which only has one orbital, a second electron shell, which has 4 orbitals, and a third electron shell, which also has 4 orbitals. So let's start adding our electrons. The first shell with only one orbital can only carry 2 electrons. The second shell can carry a total of 8. Should have used a different color because these are negatively charged, so don't get mixed up with my colors. Okay, so now we have a total of 10 electrons, so now we need 7 more in the outermost shell, or the valence shell. So now, if you look, in order for this atom to complete its valence electron shell, it's missing only 1. So it is most likely going to steal or share an electron from somebody else. And the beautiful thing about chlorine and the atom we just discussed, sodium, is that sodium gave up an electron and chlorine wants an electron. So chlorine ends up stealing an electron from sodium. And because it stole an electron from sodium to complete its valence shell, it now has more electrons than protons, and we call it a negative ion, which is called an anion. Okay, so what we saw in the past couple slides with sodium chloride is we saw a give and take mechanism. And the give and take mechanism was giving up electrons led to a positively charged ion, and taking electrons led to a negatively charged ion. And what happens afterwards is then those ions are attracted to each other. And that attraction causes what we call an ionic bond, because suddenly we have a positively charged ion and a negatively charged, and we have opposites attract. So the bond actually is a result of the different charges of the 2 ions. It is not the actual exchange of the electrons. So an ionic bond involves an atom that gives up an electron and an atom that takes an electron. Okay, and then as a result of that exchange, you have a positively charged cation and a negatively charged anion, and they are attracted to each other. That is the bond, that attraction. It's a very weak bond, and a great example is table salt, which is NaCl. And table salt easily dissolves in water because that bond is very weak, and you end up getting your sodium and your chloride ions as it dissolves in water. All right, let's take another example. So now we're going to look at oxygen, which has a total of 8 electrons. Okay, so here's our positively charged nucleus, surrounded by 1 electron shell, 2 electron shells. Okay, now if we go ahead and complete our first shell, our first 1 orbital with 2 electrons, then we can move on to our outer shell, which now we have to add our 6 electrons to get our total of 8. Okay. Now what's going on here is you see 2 empty places. The goal of oxygen is to complete its valence shell. And it could do this either by stealing an electron or 2 electrons from different atoms, or it could share them. Let's explore our hydrogen again. Okay, so our hydrogen has 1 electron. Okay, so if I were to draw this as our nucleus, and this is our electron shell, hydrogen has 1 lonely electron. And it can complete its valence electron shell by sharing an electron or by giving up an electron. And what happens is I am setting us up to look at how water forms. So I'm going to draw another hydrogen with its 1 lonely electron. And what ends up happening is when hydrogen gets a little bit closer in here to the oxygen, you can see that we share. And by sharing, oxygen then has 2 electrons here and 2 electrons here, and hydrogen has 2 electrons in its valence shell. And so now both of them are complete, and they are both happy atoms. So they have shared their electrons, creating a bond that we call covalent. It is a very strong bond between atoms. So a covalent bond is when two atoms share electrons to complete their valence shell. It's a very, very strong bond. An example is water. And what happens is it often results in a term that we call electronegativity. Electronegativity is when one atom of a molecule tends to have a stronger pull for the electrons, and therefore you end up with, I'm going to just draw my water molecule here like this. You end up with what we call a polar molecule. And a polar molecule is one where it has areas of the molecule have a negative charge and areas of the molecule have a positive, so we call it polar. That is what we refer to as electronegativity. And oxygen is a very electronegative atom. So again, electronegativity is the attraction of an atom for the electrons of a covalent bond. So if two atoms of the same element are sharing electrons, for example hydrogen and hydrogen, those electrons are equally shared. But if one atom has a stronger quote-unquote pull than another atom, like oxygen, then there's unequal sharing. We call that polarity. And that unequal sharing is simply that the electrons tend to hover around oxygen more than they hover around hydrogen, thus creating a negative side and a positive side of a molecule. Here again is a diagram of what I was attempting to draw before. Now here you see the positive part, here you see the negative part. And this is essential to understand because it basically drives all the behaviors of water. Some bonds form as a result of this electronegativity. So if we draw our water molecule again, I'll draw a couple of them. Okay, now our oxygen has more attraction for those electrons, so it's going to be negatively charged on that side. And the hydrogens, because the electrons don't spend so much time by them, we have these positive areas, so that's the polarity. And what you get then is you see what we saw in our ionic bonds, is that you have then an attraction between opposite charges. And that attraction there is called a hydrogen bond. It is not an ionic bond, it is a hydrogen bond. Okay, so in this quick video we talked about atoms, atom behavior, electrons, and bonds. Hopefully that will clarify some stuff, and when you come to lecture you'll be ready to model some of the atoms and fill up their electron shells with electrons. We'll see you tomorrow.